Dear rector, dear guests, ladies and gentlemen, I chose the topic of my presentation to broadly describe my research interest, something like last 10 years or so, and also continuing to at the moment, and I would say to the foreseeable future. So predicting structured data is the title, and in the next 20 minutes or so I'll try to give you some kind of overall picture of what this research is all about. Okay, so if I start with motivation, I guess we all know that data amounts in different areas of life are exploding all the time, have done so over the last decade, and they really have this kind of exponential growth that you see on the pictures on the right. So for example, most of us know about Facebook. Some of us are addicted to Facebook, and you see this growth curve. It's really this kind of exponential form. Similarly, Wikipedia, this online encyclopedia, has similar kind of growth term. And if you go to scientific area, so biological domain, here on the right we have this size of the UniProt database. That's one major biological database. It has similar kind of really steep growing curve. So the amount of data that is increasing in these fields of life, of course, enables new applications. So in science we get new possibilities, but also in our daily lives we can create applications that would not be possible without this data. So my own research field, machine learning, is one of the key approaches when we want to convert these data masses to intelligent adaptive models, which in turn fuel these applications. And one quite important theme underlying this research are efficient algorithms. So we need efficient algorithms to process the data in reasonable time. So the data masses are so large that we need to have efficient techniques for processing. At the same time, if we want to have kind of fast, responsive applications, we need to have efficient algorithms so that we can make, for example, predictions on the fly, so to speak. And last, but definitely not least, is energy. So the bottom picture here is actually some kind of prediction of consumption of energy by this US Environment Protection Agency, EPA, energy consumption of data centers around the world. So this is actually a little bit old picture, but you can see this kind of similar kind of growth trends that, if you think about environment, are pretty worrying. That actually our computation is starting to use huge amount of energy. So one kind of motivation for efficient algorithms would be to actually stem this growth of energy as well. All right, so this is the kind of the setting, the motivation. So my kind of particular topic is structured data, and I guess I need to first tell you what I mean when I say structured data. So of course I'm talking about the logical structure, so logical relations between data items. So and here I have three examples of different kinds of logical structures you can have between data items. So yes, okay. So we have first sequential data. So here, for example, it's a DNA molecule. So that's very abundant type of data. So this is example of a Wikipedia article. That's another type of sequential data. So this is just a natural text where we have kind of a sequential structure. So the second type of structures of interest are hierarchies. So here I have the printout of the old drawing by Charles Darwin. So this is the sketch from his notebook of Tree of Life that he sketched in the 1800s. Below is a bit more newer example of a hierarchy. It's a internet directory, so a website that categorizes different kind of websites in hierarchical form. So here it's not very obvious, but you have this kind of hierarchical structure here. You go down the levels of this hierarchy, and here are some items on this level. Okay, and the final type of structures are networks. Here in the upper right-hand side, I have an example of a biological network. So this is actually a metabolic network that tells how kind of cells kind of information processing is structured. And then final example, of course, are social networks, like I mentioned Facebook, and there are some other ones as well that also have this kind of network structure. So why I am interested in structure, I have kind of two goals. So we want to make models both faster by utilizing cleverly these structures in the data, but also more accurate. So we want to make the models also better by utilizing this structure. Okay. So here's a little bit more kind of detailed view of what kind of models I'm talking about. And here is a little bit of math. I'm not going to go very deep into the mathematics, but I guess this is the level we need to have in order to understand what we are talking about. So basically we are building models from the data of this type. We have some function of two arguments where X and Y are both some objects, both may be structures, both may be sequences, maybe hierarchies, maybe networks. And basically what we want to do is, based on knowledge of X, predict what is the corresponding output side. As training data, we assume that we have a large set of examples of this similar form. So we have a set of pairs, X and Y, which we can use to train our models with. And given this data, we have some learning algorithms that search for an optimal model of this kind. I think this laser, oh yeah, it still works. Okay, so now it's fading. I think the battery must be on, but there's another one. Hopefully this is brighter, yeah. All right. So we want to search for kind of best model in a large set of models based on this training data. And there are different computer algorithms that then try to make this thing work. So basically to make the optimization, the search in this set efficient, and also the predictions accurate. So get statistically best models we can get. All right, so this is kind of the kinds of models we are interested in. And next I have a couple of examples what kind of applications can be achieved with this kind of models. So actually these are also kind of chronological order in what I have been affiliated with. So this is the kind of the oldest of the three examples. So here the application is automatic document classification. So we have, for example, a news document of some topic, and then we have a taxonomy or a hierarchy, and we want to predict what are the correct classes this document is supposed to belong to. So on the right, I have this taxonomy, and this green part in the taxonomy is the correct, supposedly correct labeling of this document, so correct classification of the document. So we have this kind of two parts, starting from the root of the hierarchy and going up until up to certain internal nodes, and they stop, so they are not more specific than that. Okay, so and this is one of the examples. Another one is a statistical machine translation. So I guess many of you have heard or even used Google Translate. So Google has this server where you can input data in some language, and this server will give a translation in some other language. And behind this server is a statistical model that basically follows the same form I was showing you on the last set, and similar principles as well. Of course, there are lots of detail that does not fit here. So this is one application, and below here actually is something that we have done in our research group. So this is cross-lingual information retrieval. So basically, the idea here is that you can have this multilingual search tool. So you have a server where you can make queries in your own language to some database that's in some foreign language you don't need to understand, or you maybe don't understand. And you can retrieve documents from this database, which are then again translated back to your own language. So that kind of technology is possible with this kind of structured prediction models. Okay, then I have one more example. So this is in bioinformatics. It's quite a challenging task. So what we have here as input are different kind of measurements from the biological phenomenon. So for example, this is measurements that give you the DNA sequence of some organisms, and here another type of data gives the expression states of the genes, so which genes are on in particular conditions and which are not. And then there are other kinds of data, further kinds of data that we can use. So our goal would be to use this data to reconstruct the underlying biological network that caused this data to appear. So this is kind of the reverse engineering that biological system. So this is a main kind of output, and this is quite a challenging task. And we actually have a new project at the moment where we are concentrating on this application. Okay, so here's kind of a couple of applications for you to get motivation. And now I'm going to show you a little bit a peek under the hood. I cannot give you any details. It doesn't fit into this presentation, but I will show you kind of a couple of principles that we can use in these models to make them work. And maybe the most important concept or idea behind many of these models is idea of co-occurring features. So we have some features of our input data and output data that we always or often seem to see together. And we can learn something from that. So I just give here an example. So we had this document classification problem, and here it's just an excerpt from the document like this. So this is the title of the document, and then we have the correct categories of that document. And what are these co-occurring features? There are just something I can pick from here and at the same time pick something from here. So for example, football bandit is a prefix here, and news sport is a partial label that this document has. Or another example here, bandit accuses is another bit of text, and there's another pair of classes in the hierarchy that co-occurs with that. So you can imagine we have many possibilities to generate these pairs. In fact, we can have millions of this kind of co-occurrences. So we are talking about pretty large models in reality. And what we do with these features, we learn some kind of importance weights. So how important is this that we saw football bandit and news sport co-occur in the data? And there are different algorithms. I won't go into the details of these algorithms, but kind of the outcome will be that probably we'll have high weight for this kind of feature. It somehow tells something important about the document. And at the same time, there might be features that are not important, and they will have zero weights in the model. And how do you make this compatibility score? It's after this huge set of co-occurring features, I sum together the feature weights I obtain for the pair. And now kind of I can interpret this compatibility score as like this, that my X and Y are the more compatible, the more important features they share. And so this is very abstract kind of description of actually quite large set of machine learning algorithms that in different ways use these kind of principles. Okay, so I will still show you a little bit of these methods. So I kind of promised you that I want to use algorithms to make my models faster and more accurate. So I try to give you an example here how this is going to happen. And first I will show you a kind of example how we can utilize the structure to make models faster. So here I again use the same example, this document classification problem. I have relatively medium-sized data sets of these documents in relatively large taxonomy. So I only have this small toy taxonomy here, but in reality taxonomy is a little bit larger. And I have two algorithms. First one, it's called dynamic programming. So people that are from computer science know what I'm talking about when I say dynamic programming. You don't need to know more that this is an algorithm that knows that this structure is a hierarchy. And what I'm interested in, these algorithms both can give me an update of the model. So when I want to optimize my model, I have series of updates, and these basically are two choices how I can make the update. So this is one that knows about the structure. Here's one that doesn't know about the structure. Both are actually pretty nice algorithms. They are not stupid, neither of them, but one knows that there is structure, other one doesn't. So what will happen, so this is a test. I try to optimize my model. So here is a picture on the right-hand side where the progress of optimization is shown along this vertical axis, and along horizontal axis I have time used. So how much time I have used in optimizing my models. And basically from this picture you can see all of these structure-aware algorithms. So these are different parameters for the same dynamic programming algorithm, work pretty fast compared to the algorithm that is not aware of the structure. Basically we get something like 10-fold speed up by using algorithm that knows that we are talking about the hierarchy. Okay, so this is the first part of the example. The next question was how I can make my models more accurate by this method. So basically, with this kind of structure of our methods, we can look at the correlation between nearby classes. For example, in this text classification application, we know that music and jazz probably are correlated. So the question for our models are that what are the features in the document that make it belong to music but not jazz? So how can we learn something about this? And if you have a method that does not know about the structure, it cannot really learn this kind of relations. So it's more likely to do something like predicting that it's not music, but it's still jazz. So we can have this kind of phenomenon going on. Okay, just to show you, so what happens when we have this kind of flat model and a hierarchical model. So here is F1 statistics of our predictions. So basically says how good our predictions are. And these are bars that go deeper and deeper of the hierarchy. So this is the root, and then you go lower and lower. There is one flat method, that's the blue bar, and the other four are aware of the hierarchy in some sense. And you can see that this flat method is not able to work very well when we go deep into the hierarchy, very specific classes. So we can see that this kind of being aware of the structure helps making our models more accurate. Okay, so I'm very close to being out of time, so I'm just showing you a slide of future challenges. So one big challenge is to make efficient algorithms for large-scale structured prediction. When our data sets get larger and larger all the time, we need to have better and better algorithmic techniques. And techniques like grid or cloud computing are something that are quite interesting directions to look at. And also, I mentioned you about the energy. So one interesting direction would be to think about how can we make the algorithms energy efficient. So make kind of accurate models with less energy consumption. Another one which comes very often in real-world applications is missing data. So you have somehow incomplete data of your phenomenon, and your algorithm should not break down if it happens that you don't have complete data available. And this is one kind of theoretical challenge, how to do that. And of course, finally, these applications. So I'm very much active in the biological domain, bioinformatics, but also this kind of network mobile computing is bound to give new challenges for these methods. Okay, so I'm concluding with the slide of acknowledgements. So science doesn't happen, by working in a chamber by yourself. So I have a large group of people that I have contributed or to the past work or will hopefully contribute to the future work. So I have a relatively small research group at the moment. Actually, I don't want to grow it too much, but maybe a little bit from this. Then there are certain number of people that have been part of our research group but now work in other places. So here, and also some center of excellences at the University of Helsinki have allowed us to do this kind of long-term research. European networks are quite well, and of course there are then a big list of academic collaborators that also have contributed to the research. Okay, so I'm done. So thank you for your attention.